In part 6 of our lesson on parametric equations, you will learn how to graph a plane curve, C, that involves trig functions. Recall that the Pythagorean identities we learned earlier this semester are sine squared of t plus cosine squared of t is equal to 1. Tangent squared of t plus 1 is equal to secant squared of t, and 1 plus cotangent squared of t equals cosecant squared of t. In these next two examples, we will use these Pythagorean identities to help us create the equivalent rectangular equation. So let's see how this is going to work. In this example, we have to find an equivalent rectangular equation, sketch C, and describe its orientation. We are given the parametric equations that x is equal to 5 sine of t and y is equal to 3 cosine of t. Our interval for t is that 0 is less than or equal to t is less than or equal to 2 pi. In order to create an equation that only has x's and y's in it, the strategy you will want to use when the parametric equations involve trig functions is to isolate the trig functions in each of the parametric equations. So this first one becomes x over 5 is equal to the sine of t. And the second one becomes y over 3 is equal to cosine of t. Now, to get these two worked into an equation together, we can use the Pythagorean identity that sine squared of t plus cosine squared of t is equal to 1. And we substitute. For the sine of t, we will substitute x over 5. So this is x over 5 squared plus, for cosine of t, we can substitute y over 3. We have to square that and set it equal to 1. So this becomes x squared over 25 plus y squared over 9 is equal to 1. Because both the x and the y are squared, and there is a plus sign between them, we recognize that this will be an ellipse. Analyzing the equation, we see that the center of the ellipse is going to be at 0, 0. The horizontal axis will be the square root of whatever's under the x, which is 25. So that's 5. The vertical axis is going to be the square root of whatever's under the y, which is 9. So that's a 3. Next, we will use a dotted line to draw the ellipse, because remember, at this point, we don't know if C will travel the entire ellipse or only part of the ellipse. So starting from the center, which is at 0, 0, we know we go out 5 in the positive direction and negative 5 in the negative direction. On the y-axis, we will go up by 3 to positive 3 and down by 3 to -3, and we can dot in the curvature of the ellipse. While we don't know how much of the ellipse the plane curve will travel, we know that it does have to travel on that ellipse, either some of it or all of it. We've learned that the way we can determine how much of it travels is using the interval for t. So t we know that x is going to equal 5 times the sine of t, and y is going to equal 3 times the cosine of t. We know that t has to go from 0 to 2 pi, so I'm going to go for the easiest possible values I can use to sort of span that whole interval, and that's the quadrantal angles. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, if that doesn't tell me enough information, I can always choose to plug in points in between if I need to. But let's start off with the easiest values and see if we can plot those points and get the curve. If t is equal to 0, then x is going to be 5 times the sine of 0, and the sine of 0 is 0, so we know our x value is going to be 0. Our y value has to be 3 times the cosine of 0, so that's 3 times 1, which is equal to 3. So we know that our plane curve is going to start at the point 0, 3. Next, we plug in t is equal to pi over 2, so our x value will be 5 times the sine of pi over 2, which is 1. So our x value is 5. Y is going to be 3 times the cosine of pi over 2, which is 0. 3 times 0 is 0. So the plane curve C will travel along the ellipse to the point 5, 0, right here. And we know that it is traveling in this direction. If we plug in t is equal to pi, then our x value will be 5 times the sine of pi, which is 0, so x is 0. Y will be 3 times the cosine of pi, which is -1. So our y value is -3. So from here, it travels along the ellipse down to 0, -3. So we can go ahead and fill that in and indicate the direction. At 3 pi over 2, our x value will be 5 times the sine of 3 pi over 2, which is -1. So x is -5. The y value will be 3 times the cosine of 3 pi over 2, which is 0. So y is equal to 0. We can see that's right here. So the curve continues along, traveling the architecture of the ellipse. We indicate the direction. Finally, we plug in 2 pi. Our x value will be 5 times the sine of 2 pi, which is 0. 5 times 0 is equal to 0. To find the y value, we take 3 times the cosine of 2 pi. We know the cosine of 2 pi is 1, so our y value is 3. So C will travel along the ellipse to get back to 0, 3. In this direction, and it's going to end at the same point that it began. So when we describe the orientation, we would say something like C travels along the entire ellipse x squared over 25 plus y squared over 9 is equal to 1. We need to talk about the direction, and you can see from the arrows it's going clockwise, starting and ending at the point 0, 3. In this example, we have to find an equivalent rectangular equation, sketch C, and describe its orientation. We are given the parametric equations that x is equal to 2 cotangent of t and y is equal to 3 cosecant of t. The interval we are given is that t has to be between 0 and pi. We know that our strategy for these types of parametric equations is to isolate the trig function in each of the parametric equations. So the first one becomes x over 2 is equal to cotangent of t. The second is y over 3 is equal to cosecant of t. We have a Pythagorean identity that relates these two trig functions. We know that 1 plus cotangent squared of t is equal to cosecant squared of t. And now we can substitute. So this becomes 1 plus, instead of cotangent, we are going to put x over 2 quantity squared is equal to, on the right hand side we will substitute for cosecant and put instead y over 3 quantity squared. So we have 1 plus x squared over 4 is equal to y squared over 9. Next, we will take the x squared over 4 and bring it over to the right-hand side, so it becomes 1 is equal to y squared over 9 minus x squared over 4. Now the reason I knew to do that rather than bring the y squared over to the left-hand side and move the 1 over to the right-hand side is because if I took the 1 and moved it to the right-hand side, it would become -1. And none of the standard forms of the equations have a -1. They all have to have a +1. So we can leave it in this form, or if you want to write it in the little bit more familiar form, we just switch the left-hand side and the right-hand side, and this becomes y squared over 9 minus x squared over 4 is equal to 1. Now, because of that minus sign and both variables being squared, we know that it's a hyperbola. Because the y comes first, we know that it is a vertical hyperbola. We know that the center is at the origin, 0, 0. The horizontal axis comes from what is under the x variable, so square root of 4, which is 2. The vertical axis comes from what is under the y variable, square root of 9, which is 3. Now we use the horizontal axis and the vertical axis to make our box. So in the x direction, we are going to +2 and to -2. In the y direction, we're going to +3 and -3, and we make the box. The asymptotes will have to go through the corners of the boxes. Both of them have their y-intercept is the point 0, 0, so that really makes a simple equation to come up with. This first asymptote we know will be y is equal to, starting from the center, we see that we go up by 3 and to the right by 2, so the slope is 3/2, and then we multiply that times x. For this asymptote, we start at the origin and go down by 3 to the right by 2, so that's going to be y is equal to -3/2 x. This is a vertical hyperbola, so we know that it's going to look like this. And again, I'm only dotting it in because I don't know how much of the hyperbola the plane curve will travel. To find out if it does the entire hyperbola or only part of the hyperbola, we have to use our t interval. We know x is going to be 2 times the cotangent of t, and y is going to be 3 times the cosecant of t. Now notice that t cannot equal 0. T has to be bigger than 0. And likewise, t cannot equal pi. T has to stay less than pi. We don't know exactly how many points we'll need to plug in. Picking some fairly easy points between 0 and pi, maybe I would choose pi over 4, pi over 2, and 3 pi over 4. If I need to, I can always plug in more. Now x is going to equal 2 times the cotangent of t. So 2 times the cotangent of pi over 4 is equal to 1. So I know my x value will be 2. The y value is going to be 3 times the cosecant of pi over 4. Now we know that the sine of pi over 4 is radical 2 over 2. And if we take the reciprocal of radical 2 over 2, we get radical 2. So the cosecant of pi over 4 is radical 2. Now radical 2 we know is about 1.4, so we're doing 3 times 1.4 to approximate it here, which is 4.2. So looking at our graph, we would need to plot the point 2, comma, 4.2. And that actually makes sense on the graph. We come over here to 2 and then go up by 1, 2, 3, 4.2. That's going to be right here. Next, we plug in t is equal to pi over 2. For the x value, we have 2 times the cotangent of pi over 2 is 0. So this becomes 0. For the y value, we have to do 3 times the cosecant of pi over 2, which is 1. So our y value is 3, and we know that the plane curve now travels to the point 0, 3, which is right here. So we know that it's going in this direction between those 2 points. If we plug in 3 pi over 4, we get that x is equal to 2 times the cotangent of 3 pi over 4, which is negative 1. So our x value is negative 2. To find the y value, we will do 3 times the cosecant of 3 pi over 4, which is radical 2. We already know what this calculation is. We did it a few minutes ago, so we know that that's going to be 4.2. So stepping over to our graph, we would plot the point negative 2, comma 4.2, which is here. See, the graph is traveling this way. Now let's get a sense of what is happening on the graph here. We know that t has to be between 0 and pi. And if we look at our y value, which is 3 cosecant of t, we know that cosecant between 0 and pi is always positive. It's impossible for the cosecant to ever give a negative value when we are in quadrants 1 and 2 on the unit circle. We know that our y values are going to always be positive. Now we only plugged in these 3 values, but remember, pi over 4 is not the starting point. This thing starts infinitely close to 0. Now, because the direction of the curve we could tell is this way, that means combining that with the fact that we know that our y values are always positive, it means that c travels along the upper branch of the hyperbola in this direction. So notice I don't put an arrow going in the wrong direction here. C is traveling in one direction only, going this way. So to describe the orientation here, we could say C travels along the upper branch of the hyperbola y squared over 9 minus x squared over 4 is equal to 1, starting along the y equals 3/2 x asymptote and ending along the y equals negative 3/2 x asymptote. That's kind of a wordy one, but since it's not in circular motion, we can't really say clockwise or counterclockwise. So I think this is the best way to describe it. So there you have the plane curve, C. It only did the upper branch because since the t interval was between 0 and pi, we knew that meant our y values, which were based on the cosecant of t, would always be positive. So it's impossible for the graph to come down here where the y values would have to be negative. I just wanted to give you a quick heads up that in my math lab, you may need to solve for the upper branch equation versus using the full equation of the hyperbola. So we know it starts out as y squared over 9 minus x squared over 4 is equal to 1. And if we wanted to solve for the upper branch equation, we would first add the x squared over 4 to both sides. Next, we would cross multiply the 9 and then distribute that 9. So now we have y squared is equal to 9/4 x squared plus 9. Then we would apply the square roots property to get that y is equal to plus or minus the square root of 9/4 x squared plus 9. And now we would choose the positive square root because it is the upper branch that we are seeking. So in your My Math Lab homework and quizzes, you may need to look for that upper branch equation of y equals positive square root of 9/4 x squared plus 9. Now on your exams in class, it's fine with me for you to use the full equation of the hyperbola as long as in your sentence you say that it is only the upper branch of that equation. It will also be okay if you choose to go ahead and do the algebra to get the upper branch equation, but I won't require you in class during your exams to take that extra step there. But I just wanted you to be advised that in your My Math Lab homework and quizzes, there will be problems where they want you to go ahead and solve for the upper branch, or in other cases, the lower branch or the right branch or the left branch.